Okay, so let's talk about a few important equations that we'll see popping up here and there. So for many years, physicists understood the difference between light and matter. Light behaved as a wave, and matter didn't. It was little bits of matter. Then we began exploring the photoelectric effect. In the photoelectric effect, rays of light strike a material, and in doing so, every once in a while, an electron is dislodged from that material and goes shooting off. So we learned that if we put another plate to catch that electron and wired the two together, the absence of the electron on one plate and the addition of it on the other meant that there was a voltage potential and we could get electricity. We also wanted to understand how much kinetic energy those electrons had when they came off and how that changed based on what kind of light was hitting the plate. And that's when we learned something very strange. The intensity of the light hitting the plate didn't change the kinetic energy that the electrons coming off of that plate had. To put that into perspective, that would be like you deciding to throw a ball, but no matter if you throw it very soft or throw it very hard, it always travels the same distance. Instead, what we found was pretty shocking. The kinetic energy was dependent on the frequency of light that was hitting the plate. No matter how much light we shone on the plate, it didn't change the kinetic energy. But if we changed the frequency of the light, then we changed the kinetic energy. Then in 1905, Einstein came along and came up with a solution for why we were seeing what we were seeing. Einstein said that light wasn't coming just in waves like we had always thought, but that it had little tiny bursts or packets. And therefore, what changed the intensity of the light was the number of packets that were actually coming. And that the energy that light had was equal to some coefficient, denoted by h here, multiplied by the frequency. And in case you haven't seen it before, the symbol in this equation is called nu, and it's just a shorthand way of saying frequency. And so the kinetic energy was equal to this coefficient multiplied by the frequency minus the amount of work that it took to knock the electron off of the plate. And that was why the kinetic energy of the electrons being generated in this photoelectric effect were dependent upon the frequency of the light, not the intensity. So these packets of light that Einstein described are what later became known as photons, and in fact he won a Nobel Prize for his work on that. So let's talk about waves for a moment. We know that the energy of a wave is equal to c times p. You've probably seen it before, but c is just a shorthand way of saying the speed of light, and p is just a shorthand way of saying momentum. We also know that we can get the speed of light by multiplying lambda times nu. Again, if you're not familiar with these terms, the lambda is just a shorthand for wavelength, and as discussed earlier, nu is just a shorthand way of saying frequency. I've seen some people get confused about the difference between wavelength and frequency. So if you look at the wave that I've drawn here, I've put 2 marks through the center of the peaks. The distance between these 2 marks is the wavelength. Now if we imagine this wave was moving to the right, the amount of time that it would take one cycle to pass a single point is its frequency. Assuming nothing else changed, we could also envision it by thinking of the peak on the left, the amount of time that it took for it to take the same place as the peak on the right. So getting back to our equation, if we expand c, we have E equals lambda times nu times p. Or, in other words, the energy equals the wavelength times the frequency times the momentum. And as we found out earlier from Einstein's work on the photon and the photoelectric effect, we found that energy is equal to some coefficient times the frequency. So that means we can combine these two and say that some coefficient times the frequency equals lambda times nu times p. which also means we could divide out the nu, which means that this coefficient is equal to lambda times p, or the wavelength times momentum. And again, we can do the same thing and divide out lambda, and therefore say that momentum equals this coefficient over lambda. So what is this coefficient we've been talking about? It turns out that it's Planck's constant. And Planck wasn't too happy about this, by the way. But now we have two pretty important equations for us in quantum mechanics. And that is that energy equals h times nu, and momentum equals h over lambda. Now, a lot of times when people talk about frequency, they're used to thinking of it in a linear sense, meaning it's a number of cycles per second. However, in quantum mechanics, we often need to refer to angular frequency, which means radians per second. So where Planck's constant is concerned, we'll often be using it in terms of angular frequency. So to do that, we need to absorb a factor of 2 pi. So we take Planck's constant and divide it by 2 pi. This is known as the reduced Planck constant. And the symbol that we've used here, an h with the bar through it, is called an h-bar. And it's just a shorthand way of saying the reduced Planck constant. So we can say that omega, that's the w in this equation, and it's just a shorthand way of saying the angular frequency in radians, is equal to 2 times pi times nu. And the energy is equal to h bar times omega. And for the linear momentum, we have h bar times k, and k just means the wave number. The wave number is like frequency, but it's the cycles per distance, not the cycles per time. So now we've covered three very important equations that we see pop up a lot in quantum mechanics. And that is that energy equals Planck's constant times nu, momentum equals Planck's constant over lambda, or momentum equals h bar times k. I hope I haven't given you too much of a headache. But again, as much as I want to avoid the really complex math, there's going to be times that we talk about certain things that we just have to get into the math side a little bit. And these equations will help you to understand that a little better.